Hello there and welcome to the Sleepy Universe story, a place for curious minds to gather, relax, and learn. If this sounds good to you, you're in the right place. So, let your body rest. Let your breath slow down and your thoughts begin to drift because tonight we're exploring galaxies, not just our own, but some of the most fascinating galaxies in the entire universe. From silent dwarfs and colossal spirals to shattered remnants, still glowing from ancient collisions, we'll visit invisible halos of dark matter, black holes flickering like cosmic candles, and newborn galaxies glowing at the very edge of the known universe. Some facts might feel strange or wondrous. Others may sink in softly like the hush of a memory, but all of them are real. Each one a quiet echo from the vast and ongoing story of the universe. And if you find this journey helps you rest, feel free to like and subscribe. It helps others find these videos too. Now, if you're ready, let your thoughts float outward. Let your breath settle like starlight on a distant world and let's begin. A quasar is a galaxy whose black hole outshines all its stars. At the center of some galaxies, black holes grow hungry. As they feed on surrounding gas and dust, the material spirals inward, heating up and glowing brilliantly. When the black hole consumes matter at a high rate, it forms what's called a quasar. Quasars shine with extraordinary brightness, often outshining the entire galaxy that surrounds them. Some are visible from billions of light years away, their light cutting through cosmic time. The energy comes not from the black hole itself, but from the heat and motion of the infilling material around the black hole. Disks of gas reach temperatures of millions of degrees, jets of particles blast out into space, and for a time, the galaxy becomes one of the brightest objects in the universe. Quasars are active galactic nuclei, powered by darkness but shining brighter than a trillion suns. The Milky Way is eating the Sagittarius dwarf galaxy right now. Our galaxy is in the middle of a slow-motion feast. The Sagittarius dwarf spheroidal galaxy is a small, faint companion currently being torn apart by the Milky Way's gravity. It's already passed through our galaxy several times, each time losing more of its stars. Long streams of these stars now wrap around the Milky Way like ribbons, faint traces of a galaxy being digested. The Sagittarius dwarf isn't gone yet, but it's fading, stretched thin and pulled in by forces it can't resist. Its remains are helping astronomers understand how the Milky Way grew over time, not all at once, but through the quiet accretion of smaller galaxies. What we see in the night sky is the result of countless past events like this. The Sagittarius dwarf is just one more step in that ongoing process. Even now, our galaxy continues to change, reshaped by what it draws in. Some galaxies harbor not one but two supermassive black holes. When galaxies merge, the central black holes often don't combine right away. Instead, they form a binary system, two supermassive black holes orbiting each other, caught in a slow spiral that may take millions of years to resolve. These dual black holes are difficult to detect, but astronomers have found several. In some cases, both black holes are active, shining as separate points of light. In others, we see signs in the motion of nearby stars or in unusual shifts in emitted light. These pairs are a natural part of galactic evolution. Eventually, gravitational radiation may cause them to spiral inward and merge, releasing waves that ripple across the fabric of space-time. But until then, they orbit quietly, hidden deep in the centers of merging galaxies. They're like twin hearts beating in a single chest, rare, powerful, and full of unanswered questions. There are galaxies with no stars, only dark matter. In the deep quiet of space, there are galaxies that shine with nothing. No starlight, no clusters, not even the soft glow of gas, and yet they're real, held together not by what we can see but by what we can't. These are dark matter galaxies made almost entirely of the mysterious substance that outweighs visible matter across the universe. Astronomers found them not by light, but by gravity. These dark galaxies bend the light of more distant objects behind them, acquiring distortion that reveals their invisible mass. Some were discovered by how they subtly tug on neighboring galaxies. Others only came to light through patterns of motion, ripples left in nearby gas. No one knows how they formed. They might be failed galaxies or remnants of others long since erased, but they float through space like silent shadows, hidden islands of gravity with no light at all. The Milky Way is being stretched apart by cosmic tides. Galaxies may seem timeless, unchanging, but even ours is caught in the flow of larger forces. The Milky Way is being pulled gently but persistently by the gravity of nearby galaxies, especially the massive Andromeda Galaxy, drifting toward us across the void. These are called tidal forces, and they stretch our galaxy in slow, sweeping motions, like the pull of the moon on Earth's oceans, but on a cosmic scale. Over millions of years, this stretching has warped the shape of our galaxy's outer disk, creating subtle waves and ripples in its spiral arms. These stars are nudged from their paths. Clouds of gas shift and drift. It's not violent, just a steady reshaping of our home. Even galaxies can feel the tides of the universe, reminding us that no structure, no matter how vast, exists alone. Everything is connected, and everything moves in time. Galaxies can be over 100 times larger than ours. The Milky Way is enormous, to hundreds of billions of stars, stretching more than 100,000 light-years wide. But compared to the true giants of the universe, it's modest. Some galaxies like IC 11001 are 6 million light-years across. That's more than 100 times the diameter of our own. These giant ellipticals sit at the centers of galaxy clusters, and they didn't get so big by forming stars alone. For billions of years, they've swallowed dozens, even hundreds of smaller galaxies. Each merger added more stars, more gas, and more mass. Their cores are dense and ancient, filled with red-ink stars. Their outer regions fade slowly into darkness where lonely stars orbit in vast slow circles. These giant galaxies are rare and quiet and hard to comprehend, but they remind us that in the universe, even something as massive as our galaxy is just middle-sized. Some galaxies are forming stars 1,000 times faster than the Milky Way. Most galaxies form new stars at a slow and steady pace. The Milky Way gives rise to maybe 1 or 2 stars per year. But some galaxies go through brief, intense periods of star formation known as starbursts. In a starburst galaxy, hundreds or even thousands of new stars are born each year, fueled by dense clouds of gas collapsing under gravity. These outbursts are often triggered by collisions or merges where two galaxies pass through each other and stir up their gas. The result is a sudden blaze of activity, ultraviolet light, hot dust, glowing gas, and newborn stars lighting up the galaxy's core. But this pace can't last forever. Starburst galaxies burn through their fuel quickly, and many become quiet once the gas is gone. They shine briefly and brilliantly like cosmic fireworks before fading into calmer forms. For a little while, though, they're among the brightest galaxies in the sky. The supermassive black hole in Andromeda is twice the mass of ours. At the heart of nearly every large galaxy is a supermassive black hole, a region of space so dense and massive that not even light can escape it. Ours is called Sagittarius N*, and it sits quietly at the center of the Milky Way. It's a sieve about 4 million times the mass of the Sun. But the black hole at the center of the Andromeda Galaxy, our nearest large neighbor, is even bigger, much bigger. It's at least twice the mass of ours, possibly much more. Right now, both black holes are fairly quiet. They aren't actively consuming matter, so they don't shine like quasars. But in the past, they may have blazed. And in the future, when the Milky Way and Andromeda merge, Their black holes may spiral together and combine into one even more massive object, to galaxies, to hearts, one future black hole waiting. In the dark, we can watch galaxies as they were 13 billion years ago. Looking into deep space is also looking into the past, because light takes time to travel. The light from the most distant galaxy, east, we can see has been journeying through space for over 13 billion years. These galaxies appear as tiny smudges in telescope images, faint, redshifted, ancient. We're seeing them not as they are now, but as they were when the universe was still young, only a few 100 million years old. They are small, chaotic, full of dust and new stars. Some are in the earlier stages of formation, glowing with the light of the first generations of stars. These early galaxies helped shape the universe we see today. They ended the cosmic dark ages. They formed the seeds of galaxy clusters. They burned bright in a time when the universe was still figuring itself out. And somehow across all that time, their light has reached us. The Milky Way is surrounded by invisible stellar streams from red galaxies. Our galaxy didn't form all at once. It grew slowly over time, merging with and consuming smaller galaxies. And each time it did, it left behind subtle clues, thin streams of stars, stretched out over space like quiet trails. These are stellar streams, remnants of long-lost galaxies that were pulled apart by the Milky Way's gravity. They loop and spiral around the galactic halo, invisible to the eye, but detectable through careful observation. Some are still relatively intact, like the remnants of the Sagittarius dwarf galaxy, which we're absorbing right now. Others are so old they've become diffuse ribbons of ancient stars. Mapping these streams lets astronomers trace the Milky Way's history, like finding the fingerprints of past collisions. The sky around us is full of quiet motion, shaped by events that happened billions of years ago, and we're still drifting through the echoes of them even now. Our galaxy will collide with Andromeda and merge into one in about 4 billion years. The Milky Way and the Andromeda galaxy will crash into each other, not suddenly, not violently, but in a slow gravitational dance that will take hundreds of millions of years to unfold. From our point of view, Andromeda is getting closer all the time. Its motion through space is drawing it toward us at nearly 100 kilometers per second. Eventually, the two galaxies will pass through one another. Their stars mostly avoid direct contact, but their shapes are disrupted by gravity. Spiral arms will tangle, gas clouds will collide, new stars will be born. Over time, they will settle into one larger elliptical galaxy, a new home for both. Astronomers sometimes call this future galaxy Milky. Our solar system may survive the merger, carried into a different part of space. It's a quiet kind of drama moving at the pace of galaxies, and it has already begun. Some galaxies appear to be made of almost pure gas. Not all galaxies are filled with stars. Some, strangely, seem to have almost none at all. These ghostly galaxies are made mostly of cold hydrogen gas with few stars to light them up. They drift through the universe like dark clouds, detectable only through all the faint radio signals their hydrogen emits. Astronomers call them dark galaxies, and they're still not entirely understood. They might be galaxies that never formed stars, or they could be remnants, gaseous leftovers from past collisions, or mergers. In some cases, they might be galaxies where star formation was shut down before it even began. Whatever the cause, they represent a strange phase in galactic life, a kind of invisible potential. They have mass, structure, and motion, but without stars, they're nearly invisible. Just cold clouds floating between galaxies, waiting for something to ignite them, waiting to become what they almost were. There are entire galaxies we've only found because they warped light from behind them. Some galaxies don't announce themselves with light. They reveal themselves through gravity. When a massive galaxy lies between us and something even farther away, Its gravity can bend and distort the light from that background object. This effect is called gravitational lensing, and it's one of the most powerful tools in astronomy. Sometimes the light from a distant galaxy is bent into arcs, rings, or mirror images, and in the process, we spot the lensing galaxy, the one in front, even if it's too faint or dusty to be seen otherwise. Some of these lensing galaxies are full of dark matter. Others are quietly sitting in the right place at the right time. They turn into natural telescopes, magnifying the universe behind them. And by studying the light they bend, we learn about both galaxies, the 1D, on the lensing, and the one far behind it. Galaxies can shoot jets of matter that stretch for millions of light years. At the centers of many galaxies are supermassive black holes. When these black holes feed, filling in gas and dust, they sometimes unleash powerful jets of energy. These jets don't come from inside the black hole, but from the swirling disk of material around. Magnetic fields twist and focus the energy, launching twin beams of particles out from the galaxy's core at nearly the speed of light. These jets can stretch for millions of light years, Mach, each longer than the galaxy itself. In radio images, they look like giant glowing threads piercing the universe. The heat surrounding gas shapes galaxy clusters and influences star formation across vast distances. Some of the largest known structures in the universe are made by these jets, and they all begin from something smaller than a solar system, a tiny brilliant point where matter meets gravity and lights up the dark. The oldest known galaxy formed just a few 100 million years after the Big Bang. The early universe was dark. After the Big Bang, it took hundreds of millions of years for the first galaxies to form. Tiny structures were gas-cooled, condensed, and gave rise to stars. Some of these galaxies were chaotic, clumpy, and short-lived. Others, incredible. Why survived? The oldest galaxy we've found so far dates back to just 320 million years after the beginning of time. Its light has been traveling for more than 13 billion years to reach us. It's small, full of young stars, and already surprisingly well-formed. Observing it helps astronomers understand what the universe was like when galaxies were first taking shape. We can't see it clearly yet, as faint, red-shifted, and distant. But with each new telescope, we look a little farther, a little deeper into time. And the galaxies we find at the edge of visibility carry with them the story of everything that followed. Some galaxies are almost entirely made of stars from other galaxies. When galaxies collide or pass close to each other, they sometimes strip away stars, pulling them into long tidal tails or sweeping them into halos. Over time, these stolen stars can accumulate, and in some cases, they become the main population of an entirely new galaxy. These are called tidal dwarf galaxies, and they form from the debris of galactic interactions. Unlike most galaxies, they don't begin with a fresh collapse of gas from the early universe. Instead, they're made of stars that once belonged to something else. They don't always have much dark matter, and they may be short-lived on cosmic time scales, but for a while they shine with borrowed light like a collage of other galaxies' histories. Their stars may have come from different environments, but now they orbit together, held by new gravity. Galaxies can be destroyed, but sometimes they become something new instead. We found galaxies that seem to be rotating the wrong way. Most galaxies spin in the same direction as the gas around them. It's a natural result of how they form. As clouds of matter collapse under gravity, they begin to rotate, and that spin sets the direction of the stars that form. But some galaxies defy that pattern. Their disks rotate one way, while the stars or gas within them spin the opposite way. These are called counter-rotating galaxies. The cause is usually a merger. The galaxy may have swallowed another one, and the incoming material had its own momentum. Instead of aligning, the two motions remain distinct. In some cases, only the central region spins backward. In others, the entire disk is involved. These galaxies are, and they stand out in maps of galactic motion. They're quiet evidence that something unexpected happened long ago, a twist in time frozen in the stars. A single galaxy can host thousands of globula, or star clusters. Globular clusters are dense, spherical groups of stars, some of the oldest in the universe. They orbit galaxies like tiny satellites, each one packed with hundreds of thousands of stars. The Milky Way has around 150 of them, but some galaxies, especially giant ellipticals, have thousands. These galaxies can be surrounded by vast swarms of clusters stretching far beyond their visible edges. Each cluster is a fossil, a relic from the galaxy's earliest days, or from galaxies it absorbed. In a way, they're memory keepers, preserving the chemistry, motion, and age of ancient stars. Some clusters might even predate the galaxy they orbit, forming during the earliest stages of galactic assembly. When astronomers count and study them, they can learn how galaxies formed, merged, and changed. These tiny companions may look small, but they hold stories billions of years old, all orbiting quietly far out in the galactic halo. Some galaxies are powered by black holes that flicker like beacons. At the centers of some galaxies, the black holes are not quiet. Instead, they're actively feeding, pulling in gas and dust that swirl into a disk and heat up as they fall inward. The result is an active galactic nucleus, or in which can shine brighter than all the stars in the galaxy combined. But these aren't steady lights. Some AGNs flicker, flare, and dim on time scales of years, days, or even hours. The flickering comes from changes in how matter flows into the black hole. Sometimes the flow speeds up, sometimes it stops. In rare cases, we've even seen galaxies go from active to quiet and back again. It's like watching a distant lighthouse blink from across the ocean of space. And it reminds us that black holes, while often invisible, can become some of the brightest objects in the universe, at least for a while. The Milky Way's spiral arms might be temporary structures. Spiral galaxies like the Milky Way seem to have permanent arms, sweeping curves of stars, gas, and dust. But those arms might not be fixed. They could be patterns, not structures, like traffic jams that move through stars instead of cars. This idea is called density wave theory. It suggests that spiral arms are regions where stars bunch up temporarily as they orbit the galactic center. Stars move in and out of the arms like cars, slowing down and speeding up on a highway. The spiral shape stays, but the material inside it changes. Other theories suggest the arms might form and dissolve over time, shaped by gravitational interactions, star format, ion, or even past collisions. Either way, the Milky Way's spiral arms are not static sculptures. They're living patterns, always shifting, always changing as stars move through them like currents in a vast cosmic sea. Dwarf galaxies can orbit larger ones like moons around planets. The Milky Way isn't alone. It's orbited by a group of much smaller galaxies, dwarf galaxies, each containing only a few million to a few billion stars. These galaxies are gravitationally bound to us, slowly orbiting over billions of years. Some, like the large and small melanic clouds, are visible in the night sky. Others are so faint they weren't discovered until recently. Some of them may be the remnants of larger galaxies that were torn apart. Others could be primordial, leftover fragments from the earliest days of galaxy formation. Dwarf galaxies play an important role in the growth of larger ones. Over time, they can be pulled in, stripped of stars and gas, and eventually merged into the host. But until that happens, they orbit quietly, drifting in long arcs through the galactic halo. Like moons around planets, they're small companions, ancient travelers moving through a larger story. There are galaxies so faint, they're almost impossible to detect. Most galaxies are easy to miss without a telescope, but some are nearly invisible, even with one. These are raw diffuse galaxies, so spread out and dim that Their stars are barely distinguishable from the background of space. Some are as large as the Milky Way, but contain only a tiny fraction of its stars. They're ghost-like with very low surface brightness, often appearing as pale smudges even in deep sky surveys. Astronomers only started finding them in the past few decades, using advanced techniques to detect their subtle glow. Their origins are still debated. Some might be failed galaxies, ones that lost their gas before they could form many stars. Others might have been torn apart by gravity. Whatever their story, they float through the universe in near silence, enormous and barely visible. It's possible we've overlooked countless others, hidden in the dark. Galaxies that shine like fading breath. Entire galaxies can be thrown out of clusters like cosmic runaways. In dense galaxy clusters, gravity can create strange and violent outcomes. Galaxies pull on one another, sometimes passing close enough to exchange stars, gas, or momentum. Occasionally, these interactions go further. One galaxy can be flung out of the cluster entirely, hurled into intergalactic space at incredible speeds. These are called runaway galaxies. Some were ejected by interactions with supermassive black holes. Others were slingshotted during multiple encounters. All ejected, they become lonely travelers drifting through the void with no neighbors for millions of light years. A few leave behind long tails of gas and stars. Others carry on. Why their quiet, solitary islands in the dark. These runaways are hard to find, but we've spotted several. Each one tells a story of disruption, of close encounters gone wild. In a universe overrun by gravity, even the galaxies can be launched into exile. The core of the Milky Way may once have been as bright as a quasar. Today, the center of our galaxy is dim and quiet, but that hasn't always been the case. Evidence suggests that the supermassive black hole at the Milky Way's heart, Sagittarius asterisk, may have gone through an active phase in the past. During that time, it could have fed on large amounts of gas, lighting up the galactic core like a quasar. Traces of that activity remain. We see vast bubbles of gamma rays, the Fermi bubbles stretching above and below the plane of the galaxy, possibly blown out by past eruptions. We also detect echoes of X-ray flares bouncing off clouds near the center. It may have happened millions of years ago, long before humans existed, but the memory is still there, written in radiation. The center of our calm spiral may once have blazed briefly, turning the Milky Way into one of the brightest galaxies in the sky. Galaxies follow a hidden map of the cosmic web. On the largest scales, the universe has structure, not random, but patterned. Galaxies aren't scattered evenly through space. They gather along vast filaments, forming a network known as the cosmic web. These filaments are made of dark matter, gas, and galaxies strung together over hundreds of millions of light years. In between them lie voids, enormous empty regions where almost nothing exists. Galaxies form and move along these filaments like cities lining invisible highways. The structure of the web was shaped by tiny fluctuations in the universe, amplified by gravity over billions of years. We've mapped some of it using galaxy surveys, and computer simulations help us visualize its shape. But most of the web is still hidden, especially the dark matter that defines it. Galaxies live within this framework, growing and evolving where the filaments meet. The universe is not just vast, it's connected. Some galaxies contact in supermassive black holes that are off-center. You might expect the heaviest object in a galaxy to sit right in the middle, and usually that's true. Supermassive black holes tend to anchor the centers of galaxies, but in some cases they don't. We found galaxies where the black hole is offset, floating tens of thousands of light years away from the galactic core. These displaced giants may have been kicked during a collision. When two black holes merge, they can release gravitational waves unevenly, launching the resulting black hole like a cosmic cannonball. Other times, merger might lead to black holes orbiting each other with one drifting slightly from the center. These off-center black holes still influence their surroundings, but they move through their host galaxy. It's like hidden travelers. Finding them isn't easy. We detect them through unusual motion, bright emissions, or distortions in nearby gas. They remind us that even the centers of galaxies can shift. The light from distant galaxies is stretched into infrared by the expanding universe. Light travels across the universe at a constant speed, but the space it travels through is not static, expanding. This expansion stretches the light itself, lengthening its wavelength and shifting it toward the red end of the spectrum. For the most distant galaxies, the shift is so extreme that their visible light becomes infrared by the time it reaches us. This process is called redshift, and it's one of the key ways we measure distance in cosmology. The farther away a galaxy is, the more its light has been stretched. Some of the earliest galaxies ever observed are visible only in infrared, their ancient starlight dimmed and reddened by the growing fabric of space. We use special telescopes, like the James Webb Space Telescope, to see then these galaxies are still glowing even after more than 13 billion years. The universe itself has changed their light, but not erased it. We find galaxies that are still actively cannibalizing their neighbors. Galaxies don't just collide, they consume. Larger galaxies often pull in smaller ones over time, stripping away their stars and gas and eventually absorbing them entirely. This process is called galactic cannibalism, and it's still happening today. In deep sky surveys, we've seen galaxies with faint trails of stars stretching behind them, leftovers from smaller companions that are being torn apart. These tidal features are signs of recent or ongoing mergers. Some galaxies have multiple satellites in the process of falling in. Others are caught in the act of devouring a neighbor. Their structures are distorted by gravity. Our own Milky Way is doing this too, pulling in nearby dwarf galaxies one by one. Cannibalism isn't a rare event, it's a normal part of galactic growth. Galaxies live long lives, but they're always changing, always reshaping themselves, and sometimes they grow by taking in everything around them. Some galaxies are so dusty they're invisible in optical light. Starlight doesn't always reach us. In some galaxies, thick clouds of dust absorb visible light, hiding entire structures from view. These dust-rich galaxies often form stars at high rates, creating and recycling dust as they go. To the naked eye or even through standard telescopes, they may seem invisible, faint, or entirely dark. But when astronomers observe them in infrared or submit wavelengths, they glow brightly. Dust absorbs short wavelengths and remits them as heat, allowing hidden galaxies to emerge in thermal light. Some of the most active star-forming galaxies in the early universe were discovered this way. Without infrared astronomy, we might never have known they existed. These dusty galaxies are full of life, stars being born behind veils of carbon and silicates. Their glow is subtle, but it's there, and with the right instruments, we can peer through the dust and watch X-ray galaxies come into being. Galaxies in clusters can be stripped of their gas by intergalactic winds. Clusters of galaxies are not empty spaces. They're filled with a thin hot plasma. The intercluster medium and galaxies moving through it can experience a kind of pressure like wind. This wind can push against the gas inside a galaxy, stripping it away as the galaxy moves. The process is called rum pressure stripping, and it's surprisingly powerful. Galaxies falling into a cluster at high speeds can lose their gas in dramatic tails that stretch for tens of thousands of light years. Once stripped, they can no longer form new stars, and over time, they fade into quiet passive systems. We've observed these stripped galaxies in detail with long, ghostly trails of hydrogen trailing behind them. It's a reminder that galaxies are shaped not only by collisions and mergers, but by their environments. Even in the vacuum of space, galaxies can face invisible resistance and summit and they lose pieces of themselves along the way. There are galaxies that glow in X-rays from colliding hot gas. Galaxies don't shine only in visible light. In some cases, their brightest emissions come from something invisible to the eye. Hot gas colliding at millions of degrees. This often happens in galaxy clusters where individual galaxies interact and the gas between them gets compressed and heated. The result is a glow in X-rays detectable by space-based observatories. Some of the brightest X-ray sources in the universe are galactic cores where black holes heat surrounding material to extreme temperatures. Others are shock fronts between colliding galaxies or outflows from intense star formation. These X-ray glows reveal what we can't see directly: temperatures, pressure, and violent interactions happening in silence. The galaxies themselves may look peaceful from afar, but inside and between them, there can be turbulence, energy, and light far beyond human vision. It's a reminder that the universe shines across a spectrum much wider than our eyes can grasp. We can measure a galaxy's mass by how it bends light from behind it. Galaxies are massive, not just in size, but in weight. But since we can't put them on a scale, how do we know how much they weigh? One powerful method is gravitational lensing. When a massive galaxy lies between us and something far away, its gravity can bend and distort the light from that background object. The more massive the galaxy, the stronger the bend. By measuring how much the light curves, astronomers can estimate the galaxy's total mass, including the invisible mass of dark matter. Some galaxies act like natural lenses, producing arcs, rings, or even multiple images of background galaxies. The effect is subtle but measurable. It lets us weigh galaxies without needing to see every part of them. Even invisible components like dark matter leave fingerprints in the bending of light. In the quiet tug of gravity, we find the hidden structure of the cosmos. Some galaxies stretch over 1 million light-years across. The Milky Way is already enormous, but it isn't the largest kind of galaxy. Some giants, known as supergiant ellipticals, are far larger. The biggest of them, like IC 11001, stretch more than 1 million light-years from end to end. That's about 10 times wider than our galaxy. They may contain over 100 times as many stars. These enormous galaxies usually sit at the centers of galaxy clusters, where they've grown by absorbing countless smaller galaxies over billions of years. They aren't structured like spirals. Instead, they're smooth, round, and diffuse with stars spread out in all directions. Their light fades slowly with distance, blending into the surrounding halo. They're ancient, massive, and quietly dominant, shaped by a long history of collisions. Standing at the center of a cluster, they watch the universe pass around them. Silent beacons in the depths of space. Our galaxy is moving at nearly 600 kilometers per second. The Milky Way may feel still, but it's not. Our entire galaxy is moving fast. Relative to the cosmic microwave background, we're speeding through space at nearly 600 kilometers per second, or over 1 million miles per hour. That motion includes the orbit of the solar system within the galaxy, the Milky Way's movement toward the Andromeda Galaxy, and the local group's drift toward a massive region called the Great Attractor. We don't feel this motion because everything around us is moving with us, but we can measure it through tiny shifts in the cosmic background and radiation, and in the velocities of distant galaxies. Space itself isn't a fixed stage. It's dynamic, and we are part of that motion. In every moment, we're hurtling through the cosmos on a path shaped by gravity, surrounded by stars, and carried forward by the quiet momentum of the universe itself. The local group contains more than 50 galaxies. The Milky Way doesn't live alone in the universe. It's part of a small galactic neighborhood called the local group, a gravitationally bound collection of more than 50 galaxies spread across about 10 million light-years. The largest embers are the Milky Way and the Andromeda Galaxy, followed by the Triangulum Galaxy, The rest are mostly dwarf galaxies, small faint systems with only a few million stars each. Some orbit the big ones like satellites, others float more freely in the group's outer regions. These galaxies interact over time, pulling on one another, merging, exchanging stars. The local group itself is just one part of a much larger structure, the Lynarchius supercluster. But even on that vast scale, the local group is our immediate cosmic family, a quiet gathering of galaxies moving together through space, each one with its own story, yet bound to the others by invisible threads of gravity. The largest galaxy in our group is not the Milky Way, it's Andromeda. The Milky Way is big, but it's not the biggest in our neighborhood. That title goes to the Andromeda Galaxy, a spiral galaxy over 2 million light-years away and roughly twice as massive as ours. It's similar in shape with sweeping arms and a central bulge, but contains more stars, a larger black hole, and a broader halo. Andromeda and the Milky Way are the two dominant members of the local group, and they're on a slow collision course. Right now, Andromeda is approaching us at around 110 kilometers per second. When the two galaxies merge in a few billion years, they'll form an even larger elliptical galaxy. Andromeda may appear as a faint blur in the night sky, but it's a vast, intricate system full of stars, planets, and mysteries. In many ways, it's our galactic twin, and someday will become part of our galaxy's future self. Some galaxies are surrounded by halos of invisible particles. On every large galaxy is something we can't see, the dark matter halo. It doesn't emit light, reflect it, or absorb it, but it exerts gravity. These halos extend far beyond the galaxy's visible stars, enveloping it in an invisible sphere of mass. Astronomers discovered them by measuring how galaxies rotate. Stars near the edges move faster than they should unless there's extra mass holding them in. That hidden mass is dark matter, a mysterious form of matter that outweighs normal matter in the universe by more than 5 to 1. Galaxies wouldn't hold together without their halos. They likely formed inside them, drawn into shape by the gravity of some something that's still not fully understood. We can't see these halos, but we know they're there. They shape galaxies, cluster them, and help form the cosmic web. The universe is held together by things we haven't yet seen directly. The melanic clouds are two dwarf galaxies orbiting the Milky Way. If you live in the southern hemisphere, you might have seen two strange patches of light in the night sky. They're not clouds, they're galaxies. The large and small melanic clouds are irregular dwarf galaxies that orbit the Milky Way. They're close by, cosmically speaking, about 160,000 and 200,000 light-years away, respectively. Both contain millions of stars, clusters, and clouds of gas. The large melanic cloud is home to one of the most active star-forming regions nearby, the Tarantula Nebula. These two galaxies are likely newcomers to our galactic neighborhood, possibly captured within the last few billion years. They're not just companions. They're also interacting with each other. Their orbits are complex, and gravity is pulling stars and gas from them as they circle the Milky Way. For now, they remain separate, brilliant, and irregular, drifting close. But over time, they may be drawn in and absorbed. Those clouds leave trails of stars behind them. As the melanic clouds orbit the Milky Way, they leave behind cool-eyed evidence of their journey, long, faint trails of gas and stars stretching across the sky. These trails form as gravity from the Milky Way tugs on the smaller galaxies, stripping material away. The most famous of these is the melanic stream, a thin ribbon of hydrogen gas that wraps behind the two galaxies and stretches for hundreds of thousands of light-years. There are also stellar streams made of individual stars pulled loose from their original home. These trails help astronomers map the shape of the Milky Way's gravitational field and tell the story of how galaxies interact over time. They're like footprints, subtle, fading, but revealing a path taken through deep space. Though the melanic clouds are still intact for now, these streams remind us that galactic warp, its aren't simple. They leave long drifting echoes. Behind them, galaxy clusters are bound together by vast quantities of dark matter. Clusters of galaxies can contain hundreds or even thousands of members, all bound together by gravity. But when astronomers measured the visible mass, the stars, gas, and dust, it wasn't nearly enough to hold the cluster together. Something else and to be providing the gravity. That something is dark matter. Though invisible, dark matter makes up most of the mass in galaxy clusters. It holds the galaxies in place and slows their motion so the sea luster remains stable. We can't see it directly, but we can detect its presence, the way galaxies move, the way light bends as it passes through the cluster, and the temperature of the interclust. A gas all point to an enormous hidden mass. Without dark matter, these clusters would fly apart. Instead, they've remained bound for billions of years, islands of light in a dark ocean. Held together by gravity we cannot yet explain. There are superclusters made of thousands of galaxies. Galaxies gather into groups. Groups collect into clusters, and those clusters in turn are part of something even bigger, superclusters. These are the largest known structures in the universe, sprawling regions filled with thousands of galaxies connected by gravity and shaped by the underlying framework of dark matter. They stretch for hundreds of millions of light years. Some are shaped like walls, others are arranged like filaments or webs. They aren't solid objects, but loose associations of galaxies moving through space together. Some are collapsing inward, others are expanding. Our own Milky Way belongs to one of these superclusters, and it's not alone. In every direction we look, we see superclusters. Beyond superclusters, reaching out across the observable universe, these massive structures took billions of years to form, sculpted by gravity acting on slight imbalances left from the Big Bang. They're not just big, they're boundaries between vast cosmic realms. We live in the Lanius supercluster, a name that means immeasurable heaven. In 2014, astronomers redefined the boundaries of our galactic neighborhood. They found that the Milky Way, the local group, and many nearby galaxy clusters are all part of a much larger supercluster, Laniakea. The name comes from Hawaiian lani meaning heaven and a meaning spacious or immeasurable. It's a fitting name for a structure more than 500 million light-years across containing over 100,000 galaxies. Laniakea isn't shaped like a sphere. It's a network of filaments with galaxies flowing along invisible lines of gravity toward a central region called the Great Attractor. This is the gravity well that guides much of our motion through the universe. Lania redefined our sense of where we live, not just in a galaxy or a group, but in a supercluster of extraordinary scale. It's a reminder that even our vast Milky Way is part of something larger, hidden and quietly beautiful. Galaxies align along filaments that stretch across the universe. When we map the positions of galaxies on the largest scales, they don't appear randomly scattered. Instead, they form a vast interconnected structure known as the cosmic web. Galaxies gather along thin thread-like filaments of dark matter and gas stretching across hundreds of millions of light-years. These filaments connect clusters and superclusters, weaving a web with glowing nodes of galaxies at the intersections. In between the threads lie immense voids, vast regions nearly empty of galaxies. The shape of this structure was seeded in the earliest moments of the universe, sculpted by the pull of gravity. Over billions of years, galaxies form where matter gathers, and they move along these hidden strands like travelers on unseen roads. When we look out into space, we're seeing not just stars and galaxies, but delicate and immense patterns that stretch far beyond what we can observe. The universe has structure, even in silence. In between these filaments lie voids nearly empty of matter. Universe isn't packed full of galaxies. In fact, most of it is almost entirely empty. Between the great filaments of the cosmic web are vast voids, immense dark regions that contain very little matter. Some are tens or even hundreds of millions of light years across. A few stray galaxies may drift through these regions, but for the most part they are silent. These cosmic voids are the emptiest places we know. They formed naturally as matter in the early universe together, leaving behind underdense areas. Studying voids helps astronomers understand the expansion of the universe and the behavior of dark energy. In a way, the voids define the cosmic web just as much as the galaxies do. They are not just the spaces in between, they are part of the shape of the whole. Quiet, dark, and nearly untouched by time, some galaxies lie in complete isolation, cosmic hermits in the void. Most galaxies live in groups or clusters, surrounded by neighbors and shaped by their interactions. But some galaxies live in solitude. These are field galaxies, systems that drift alone in space, far from any cluster or filament. Some are found on the edges of voids and others exist deep within them, without nearby galaxies to pull or collide with. They evolve more quietly, forming stars at their own pace. Their shapes are less likely to be disrupted, their gas undisturbed. We don't know exactly how these cosmic hermits formed in such lonely places. Some may have been ejected from clusters long ago. Others may have formed in low-density regions from the start. Whatever their origin, they move through space with no close companions. In a universe where so much is connected, these isolated galaxies remind us that even on the grandest scale, solitude still exists. The Hubble Space Telescope revealed galaxies in every direction we look. When the Hubble Space Telescope was launched, no one was entirely sure what it would see. In the late 1990s, astronomers pointed it at a seemingly empty patch of sky, a region with no bright stars, no known galaxies, nothing of note. They left it observing for days. What came back was astonishing. Thousands of galaxies packed into a tiny dot of space. This became the Hubble Deep Field, and later the Ultra Deep Field. It showed that no matter where we look, space is full of galaxies. Every pinprick of sky holds multitudes stretching back billions of years. Some were large, bright, others tiny and ancient, but together they revealed the richness and depth of the universe. The images changed our understanding of the cosmos. What once seemed empty was full of light, structure, and time. The deeper we look, the more we find. The deepest images ever taken show thousands of galaxies in a tiny patch of sky. Imagine holding a grain of sand at arm's length. That's about the size of the sky covered by the Hubble Ultra Deep Field. And within that tiny space, we see nearly 10,000 galaxies. Each one is filled with stars, planets, and history. Some are nearby and bright. Others are faint smudges, ancient galaxies whose light has traveled more than 13 billion years to reach us. Taken together, they offer a glimpse into cosmic time. From the early days of galaxy formation to the present, the image is a layered history, cross-section of the universe, and it tells us something profound. If a patch of sky that small holds so many galaxies, the universe must contain hundreds of billions in total. These deep images are more than photographs. They're time machines, letting us see the past and reminding us how much remains to be discovered. Quasars were more common in the early universe. Today, quasars are rare. Most large galaxies, including our own, have quiet black holes at their centers. But in the early universe, quasars were everywhere. Young galaxies were rich in gas, and their central black K-holes had plenty to feed on. During that time, many black holes grew rapidly, blazing as quasars for millions of years. Some of the brightest we've observed existed when the universe was less than a billion years old. We see them now as they were then, tiny, distant points of light that once lit up entire regions of space. Their powerful radiation affected their surroundings, altering the structure of galaxies and halting star formation in some regions. Eventually, their fuel ran out and they went dark. What remains are quiet galaxies, the relics of once burning cores. Quasars are the echoes of a brighter, younger universe, still visible across cosmic time. Some galaxies change from quasar to quiet in just a few years. Quasars were once thought to be steady burning brightly for millions of years before slowly fading. But we've now seen galaxies where that brightness flickers dramatically, changing in just a few years. These are called changing-look quasars. One year, a galaxy might shine with the energy of an active black hole. The next it dims as if someone turned down the cosmic volume. In some cases, they seem to switch back again. Astronomers believe this flickering happens when the flow of gas into the black hole changes. Perhaps a sudden surge or a blockage or a collapse of the inner disk. Whatever the cause, it means that black holes can be much more dynamic than we thought. The heart of a galaxy can flare and fade on human time scales, not just cosmic ones, and even something as massive as a quasar can have moments of quiet and sudden light. The light from quasars can travel over 10 billion years to reach us. Quasars are among the most distant objects we can see. Their light began its journey before the Earth had formed, even before the Milky Way had fully taken shape. Many quasars we observe today lie over 10 billion light-years away. That means their light has been traveling through space for 10 billion years, crossing an expanding universe to reach our telescopes. What we see is not how they are now, but how they were when the universe was still young. That ancient light has been stretched, read, dimmed, and dimmed by cosmic time, but it still carries the signature of extreme energy, radiation from a feeding black hole that once outshone an entire galaxy. Looking at a quasar is like peering through a long tunnel in space and time. It connects us to a younger universe and to a kind of brightness we no longer see nearby. Galaxies can spin so fast that their outer stars are barely held in. Galaxies don't just sit in space. They spin. Their stars orbit the center, pulled by gravity, balanced by motion. But in some galaxies, that motion becomes extreme. Their outer stars whip around at such high speeds that they seem like they might fly off into space. What holds them in is gravity, not just from the stars and gas, but from an invisible halo of dark matter. In fact, it was this unexpected rotation, stars moving faster than expected, that first led astronomers to suspect that dark matter existed at all. Without it, the galaxies would fly apart. But the unseen mass holds them together even as they spin at hundreds of kilos. It's a quiet balancing act, motion and mass in perfect tension. The faster the stars move, the stronger the invisible arms that hold them close. Some galaxies are polar rings, disks within disks rotating at right angles. Most galaxies rotate in a simple plane like a spinning disk, but some galaxies are more complex. A polar ring galaxy has two disks, one main galaxy and another ring of stars and gas that orbits around its poles at a near right angle. These structures likely form during galaxy interactions when one galaxy passes through another and leaves behind material that settles into a separate orbit. Over time, gravity shapes that material into a flat spinning ring. The result is a beautiful rare object, one galaxy wearing another, like a halo. Studying polar ring galaxies helps astronomers understand how galaxies merge and how dark matter halos are shaped. The two rotating systems move independently like layered currents in deep space, and from a distance they look like cosmic wheels turning across two axes, elegant, stable, and quirky. There are galaxies shaped like and cosmic donuts. Not all galaxies follow the usual spiral or elliptical shape. Some have central holes, ring galaxies, where most of the stars form a loop around an empty core. These often are through collisions. When a smaller galaxy punches through a larger one, the gravitational disturbance can send waves rippling outward, compressing gas into a ring and triggering new star formation. The result is a galaxy shaped like a donut. bright around the edges with little or nothing at the center. Some ring galaxies have perfect symmetry. Others are warped or off-center, revealing the violence that shaped them. They're rare but unmistakable. Unlike spirals, these galaxies show clear evidence of a dramatic past. Yet, despite their strange shapes, they remain stable, stars rotating and in balance, like tracing the aftermath of a collision that may have happened a billion years ago. Stars in elliptical galaxies move in random orbits, not spirals. Elliptical galaxies are different from spirals. They don't have arms, disks, or flat planes. Instead, they're rounded, diffuse clouds of stars, and inside them, motion is more chaotic. The stars don't all orbit in the same direction. Instead, they move in random paths. Some in circles, others in long ovals with no overall structure. This randomness comes from how ellipticals form. Many are the product of galaxy merge. Those, when two or more galaxies collide, the organized motion of their stars is disrupted. Over time, the system settles into a more spherical shape, but without a single direction of spin. These galaxies are often older with less gas and little star formation. The light is smooth and even like a calm haze inside, though every star moves in its own way, a quiet storm of motion, held together by gravity. Some irregular galaxies look like torn clouds of light. Not every galaxy fits into a neat spiral or elliptical shape. Some seem messy, stretched, scattered, and uneven. These are irregular galaxies, and they often look like torn clouds glowing softly across the stars. Many formed after past collisions or close encounters with larger galaxies. Gravitational forces pulled them apart, disrupting any ordered structure they may have had. Others simply never developed a strong central shape, forming instead as scattered clumps of stars and gas. They're often rich in hydrogen and full of young hot stars. From a distance, they may look like broken pieces of something larger, but they are galaxies in their own right, small, chaotic, and full of activity. Some are still evolving, others may eventually be pulled into larger galaxies or settle into new forms. But for now, they drift as luminous fragments shaped more by turbulence than symmetry. Starburst galaxies burn through their fuel in a cosmic flash. In most galaxies, stars form slowly over billions of years, but in starburst galaxies, that process speeds up dramatically. These galaxies form stars at rates hundreds or even thousands of times faster than usual. The burst can be triggered by a merger, a close flyby, or a shock wave. Anything that compresses gas into dense clouds. When the burst begins, stars form rapidly, lighting up the galaxy in ultraviolet and infrared. These galaxies shine brightly, but the phase doesn't last. In just a few million years, a brief moment in cosmic time, the gas is used up and the galaxy settles down. What's left is a burst of light, a wave of new stars, and a lingering glow of hot dust. Starbursts are like cosmic firestorms, intense, beautiful, and short-lived. They remind us that galaxies, like stars, can go through moments of sudden brightness before returning to calm. Galaxies can go quiet when they lose the gas needed for star formation. Galaxies need gas to make new stars. When that gas runs out or gets stripped away, star formation slows and eventually stops. The galaxy goes quiet. This can happen naturally as stars use up the gas over billions of years, but it can also be caused by outside forces. A galaxy falling into a cluster may lose its gas to the surrounding medium. Powerful radiation from a black hole or a wave of feedback from massive stars can blow the gas out. When that happens, the galaxy enters a passive phase. Its young blue stars die out and it's left with older, redder ones. The galaxy still glows, but more softly now, no longer creating, just drifting. These galaxies are sometimes called red and dead, but they aren't truly lifeless. They're the quiet elders of the cosmos, luminous fossils of a more active past. Galactic winds can blow matter out into intergalactic space. Star formation is not a gentle process. When many stars form at once, they generate winds, powerful flows of particles, and energy that can push gas out of a galaxy. Supernova explosions add to the effect, heating the gas and driving it outward. In some cases, the galactic winds are strong enough to blow material far beyond the galaxy's boundaries into intergalactic space. This removes the raw fuel for future star formation, effectively shutting it down. Galactic winds are especially strong in starburst galaxies and those with active black holes. They shape the evolution of galaxies by regulating how fast they grow. We've observed these winds as glowy, in clouds of hot gas rushing away from galactic centers. They don't stop the galaxy from shining, but they change its future. A single burst of wind can affect millions of stars yet to be born. A breath that changes everything. Radiation from black holes can stop galaxies from making new stars. When a supermassive black hole feeds on gas and dust, it doesn't just light up, it pushes back. The energy released can heat surrounding gas or even blow it out of the galaxy entirely. This process, known as active galactic nucleus feedback, plays a major role in galactic evolution. If gas is too hot, it can't collapse to form new stars. And if it's expelled, the galaxy is left with little material to work with. In this way, a single black hole, invisible and tiny compared to the galaxy, can control the entire pace of star formation. Some of the largest galaxies stopped making stars billions of years ago, likely due to this feedback. We still see the echoes of their active pasts in the hot halos and empty cores they left behind. The center of a galaxy can be quiet, but it can also change everything around it. We can detect galaxies by the hydrogen gas that surrounds them. Not all galaxies shine brightly in visible light, but many are surrounded by clouds of hydrogen, the most abundant element in the universe. This hydrogen emits a faint radio signal known as the 21 cm line. By tuning into that frequency, astronomers can find galaxies that are otherwise too faint or too dusty to see with optical telescopes. These signals reveal a galaxy's mass, rotation, and motion through space. They also help us math out dark matter, since the hydrogen follows the gravitational pull of unseen mass. Some surveys of the sky look entirely in radio waves, building maps of hydrogen across cosmic time. In this way, we can discover galaxies hiding in plain sight, invisible in ordinary light, but quietly glowing in radio frequencies. Even the faintest galaxies leave echoes, even in silence. There is something to hear. Some galaxies glow brightly in radio waves. When we think of galaxies, we usually imagine them shining in visible light. But many galaxies emit strongly in radio waves, a form of light with much longer wavelengths. Some of the brightest radio galaxies have giant jets of particles blasting from their centers, powered by supermassive black holes. These jets stretch far beyond the galaxy's visible edge, sometimes for millions of light years. Other galaxies glow in radio because of supernova explosions or because of clouds of cold hydrogen gas. The shapes of radio galaxies can be strange, with lows, arcs, or double sources of light. Many of these features are invisible to the eye but appear clearly when seen in radio maps. By observing galaxies this way, astronomers can explore hidden structures, trace energetic processes, and study the interactions between galaxies and their surroundings. In the radio sky, the universe looks entirely different and full of quiet power. Others are revealed only in far infrared light. Some galaxies are hidden by dust, thick clouds that block visible light but let infrared light through. These galaxies, called infrared luminous galaxies, often form stars at rapid rates. The young hot stars heat nearby dust, which then glows brightly in the far infrared. We can't see these galaxies with regular telescopes, but with infrared observatories, they shine. Some of them are among the most active galaxies in the universe, but they were almost completely invisible until space Scopes like Spitzer and Herschel opened the new window into the sky. Observing in infrared lets us peer through dust and uncover what's happening inside. The birth of stars, the feeding of black holes, the dynamics of mergers. It's a reminder that galaxies don't always show themselves clearly. Some hide behind veils of their own making, glowing softly in wavelengths far beyond our sight, visible only to those who know where and how to look. Galaxies in the early universe look smaller and more chaotic. When we observe galaxies from the early universe, galaxies whose light has been traveling for over 10 billion years, they don't look like the grand spirals and smooth ellipses we see nearby. They're smaller, lumpier, and more chaotic. Some are clumps of stars and gas still coming taut ether. Others are merging, colliding, or forming stars at incredible rates. These early galaxies are still in the process of assembling themselves. Their shapes haven't settled. Their stars are younger, hotter, and more metal-poor. And yet, these galaxies laid the foundation for what would become the modern universe. Over billions of years, they grew by merging with others. By forming new stars, by settling into more stable structures. When we look at them now, we're looking at the adolescence of the cosmos. Imperfect, messy, and full of energy, galaxies are still ending their way. We can see the cosmic dawn, the first galaxies lighting up the universe. There was a time after the Big Bang when the universe was completely dark. No stars, no galaxies, cooling gas. Then slowly the first light began to shine. The first stars formed. The first galaxies took shape. This period is called the cosmic dawn, and it began about 200 to 400 million years after the Big Bang. With powerful telescopes like the James Webb Space Telescope, we're now beginning to see into that era, capturing faint, distant galaxies from the universe's earliest light. These galaxies are tiny, chaotic, and incredibly bright for their size. They formed stars rapidly, burned through gas quickly, and began to ionize the surrounding hydrogen, ending the cosmic dark ages. Every image we capture from this time is a glimpse into the universe's beginning, its first attempts at structure and light. It's a distant story, and yet it's where everything we know began. The first galaxies may have been born inside dark matter halos. In the early universe, matter wasn't evenly spread out. Tiny fluctuations in density seeded by quantum noise from the Big Bang began to grow under the force of gravity. Where those fluctuations were strongest, dark matter collected into halos, invisible clouds of mass that provided the gravitational wells needed to gather normal matter. Inside those halos, gas cooled, condensed, and formed the first stars and the first galaxies. Without the presence of dark matter, it's likely these galaxies couldn't have formed at all. Halos provided structure, mass, and protection from the turbulent early environment. We still see this pattern today. Every galaxy we observe, from tiny dwarfs to giant spirals, seems to be embedded in a dark matter halo. It's an invisible skeleton, shaping how galaxies grow and move. The first galaxies weren't just lucky, they were cradled by unseen hands. Without dark matter, galaxies would fly apart. Galaxies spin, their stars orbit the center, moving at high speeds. But when astronomers tried to calculate how much visible mass was needed to hold those stars in place, something didn't add up. The galaxies should have come apart. The stars were moving too fast for gravity alone to hold them. That's when the idea of dark matter emerged, an invisible form of mass present throughout the galaxy, providing the extra gravity needed to keep everything bound together. We can't see it directly, but its effects are clear. Without it, galaxies wouldn't hold their shape. Stars at the edges would drift off into space. The entire structure would collapse or scatter. Dark matter holds galaxies together, not just in theory but in practice. It's quiet, mysterious, and absolutely essential. Galaxies shine because of stars, but they stay together because of something we still don't fully understand. The stars in the Milky Way's halo are much older than the sun. Each in its disk, the Milky Way has different parts: a central bulge, a flat spinning disk, and a wide diffuse halo. That halo is filled with some of the oldest stars in our galaxy. These stars are ancient, many over 10 billion years old, and they move through space in long looping orbits that take them far above and below the disk. The halo contains very little gas, so it doesn't form many new stars. Its population is made up of stellar relics, quiet, dim, and old. Many of them are metal poor, meaning they formed before heavy elements were common. The stars in the disk, by contrast, are younger and brighter with orderly paths and more modern compositions. By studying halo stars, astronomers can peer into the deep history of our galaxy, into the time before the spiral arms formed, when the Milky Way was still finding its shape. Some stars in the Milky Way were born in other galaxies. Not all the stars in our galaxy have always belonged to it. Over billions of years, the Milky Way has collided with and absorbed many smaller galaxies, and when it did, it kept some of their stars. These ancient mergers left behind faint streams and clusters and scattered stars that now move through the Milky Way with unusual orbits or chemical fingerprints. Astronomers can identify them by their motion and composition. Some stars move in different directions than expected. Others are made of older, simpler elements. These stars tell stories of long lost galaxies, systems that no longer exist, but whose stars live on. The Milky Way is not just a single structure, it's a layered memory, a quiet collection of stories pulled in from the cosmic neighborhood. And even now, new stars are still arriving, carried in from galaxies slowly merging with our own. We can trace the motion of ancient mergers by mapping stellar streams. When the Milky Way absorbs a smaller galaxy, it doesn't happen all at once. The stars of the incoming system are stretched out into long curving trails, stellar streams that wrap around the galaxy like ribbons. These streams can last for billions of years, slowly fading and blending into the halo. By mapping their positions and motions, astronomers can reconstruct what happened, where the original galaxy came from, how it was pulled apart, and when the merger occurred. Some streams are broad and well-defined. Others are thin and fragmented together. They reveal a history of quiet collisions of the Milky Way, growing not through sudden chaos, but by drawing in its neighbors over time. These patterns aren't visible to the eye. They require careful measurements, long exposures, and patient analysis. But once seen, they transform our understanding of the galaxy, turning it into a map of ancient motion. Galaxies are time machines. The farther away they are, the further back we see. Light takes time to travel. So when we look at a nearby galaxy, we see it as it was a few million years ago. But when we look at galaxies billions of light years away, we're seeing them as they were when the universe was young. The farther out we look, the further back in time we go. Is makes galaxies into natural time machines. We can watch them change, evolve, and form across cosmic history, not by traveling through time ourselves, but by collecting light that has taken eons to reach us. Every telescope is a time portal, and every faint galaxy in a distant image is a story from long ago. Some are young and chaotic, others are already well-formed. By studying galaxies at different distances, astronomers piece together the life story of the universe itself, from its first sparks of light to the richly structured sky we see today. It takes the Milky Way about 200 million years to rotate once. The stars in our galaxy are not fixed. They orbit the center, each at its speed, tracing long paths through space. Our solar system, for example, is moving at about 220 km per second, completing a full orbit of the galaxy in roughly 225 million years. That means we've only gone around the Milky Way about 20 times since the Earth formed. Each orbit takes so long that entire ages of life pass in a single galactic year. Dinosaurs rose and fell during one rotation. Continents drift, stars are born and die. From our point of view, the sky seems still, but we are constantly moving. The galaxy turns like a giant wheel, and we are carried with it through a quiet spiral of stars. Time stretches wide at this scale, and motion becomes something you feel only across lives of worlds. Galaxies don't rotate like solid disks. Their outer regions move differently. If a galaxy were a solid object, its outer stars would move slower than the ones near the center, the edge of a spinning record. But galaxies aren't solid. They're made of stars, gas, and dark matter, all moving under gravity. What we see is surprising. Stars in the outer regions orbit just as fast as those closer in. This flat rotation curve puzzled astronomers until they realized that something invisible must be providing extra mass. That something is dark matter forming a halo that surrounds and stabilizes the galaxy. Without it, the stars at the edges would drift away. Galaxies rotate in complex ways, not like rigid wheels, but like loosely connected systems held in place by unseen mass. The stars dance to a deeper rhythm, set by both what we see and what we cannot, a motion that spans hundreds of billions of suns all turning together. We discovered dark matter by watching how galaxies spin. In the 1970s, astronomer Vera Rubin studied the rotation of spiral galaxies. What she found didn't match expectations. Stars far from the center were moving too quick, as if something invisible was holding them in. According to the laws of gravity, they should have drifted away, but they didn't. The only explanation was that galaxies contained far more mass than we could see. This unseen mass became known as dark matter. It doesn't emit light or energy, but it exerts gravity enough to bind galaxies together and to shape their motion across cosmic time. Today, nearly everything we know about dark matter comes from its gravitational effects. We can't see it directly, but it reveals itself through motion in the curves of spinning galaxies. We found evidence of something vast and invisible, something still mysterious, and something that might hold the universe together. Gravitational lensing has revealed galaxies we couldn't see any other way. Sometimes we find galaxies not by their own light, but by how they affect the light of others. When a massive galaxy or cluster lies between us and a more distant object, its gravity bends the background light, creating a cosmic lens. This effect, known as gravitational lensing, can reveal faint faraway galaxies that would otherwise be invisible. The lens magnifies and distorts the image, stretching it into arcs, rings, or mirrored duplicates. With this technique, astronomers have discovered some of the most distant galaxies ever seen. In some cases, we observe galaxies whose light has traveled over 13 billion years, brought into view by the mass of a foreground lens. Lensing doesn't just show us hidden galaxies. It also lets us map the distribution of dark matter. Through this bending of light, space itself becomes a tool and gravity becomes a kind of telescope. Some galaxies are strong lenses, warping and multiplying the light of background. Galaxies don't just orbit and glow. Some act as powerful lenses, bending light from other galaxies behind them. When the alignment is just right, a single background galaxy can appear as multiple images or as an arc or a ring wrapped on the foreground lens. These Einstein rings are striking symmetrical features created by curved space. The lensing galaxy can be small or massive, but it must have enough gravity to distort the path of light. The resulting image depends on angles, distance, and mass. In many cases, we don't even see the background galaxy directly, just the shape its light takes after bending around the lens. These systems are beautiful and rare. They allow astronomers to study both the distant source and the lensing galaxy itself, all in one image. In these quiet distortions, we see how light travels through a universe that is not straight but curved. Galaxies can act like natural telescopes, magnifying the distant universe. We build telescopes to gather light to see farther, deeper, and more clearly. But nature has its own telescopes, galaxies, and galaxy clusters whose gravity bends and magnifies light from behind them. These natural lenses amplify faint objects, allowing us to see things that would otherwise be lost in the dark. Some of the most distant galaxies ever discovered were found this way. Their HT stretched and boosted by massive foreground systems. These lenses reveal details we couldn't resolve otherwise. The structure of early galaxies, the formation of stars, the motion of gas. They show us the universe, not just as it is, but as it was magnified across time. The cosmos bends light with quiet elegance, and through that bending, we glimpse things far beyond the reach of our instruments alone. Galaxies made visible by gravity itself. We found entire galaxies inside gravitational arcs. Gravitational lensing can stretch the image of a distant galaxy into an arc, a long curved streak of light that wraps around a foreground mass. Some cases, what looks like a single arc turns out to contain an entire galaxy magnified and distorted by the lens. These arcs are more than beautiful shapes. They are time capsules showing us galaxies as they were billions of years ago. With careful modeling, astronomers can reconstruct the original shape and structure of the source galaxy, even measuring its star formation rate, mass, and composition. Some arcs reveal galaxies from just a few 100 million years after the Big Bang, young systems we'd never detect without lensing. These arcs are rare and delicate, and they depend on perfect alignment. But when we find them, they open a window into the deep past. In their curves, we find distant galaxies drawn out by gravity's hand. Galaxies near the edge of the observable universe are moving away at near light speed. The universe is expanding, and the farther away a galaxy is, the faster it moves away from us. This isn't motion through space, but the stretching of space itself at great enough distances. This expansion causes galaxies to recede at speeds approaching the speed of light. Near the edge of the observable universe, galaxies are so far that their light is stretched into extreme infrared or radio waves by the time it reaches us. Some may already be beyond our reach. Their light is no longer able to cross the expanding space to get air. What we see now is ancient light sent from a time when they were closer. Over time, more galaxies will slip past this cosmic horizon. The universe is not only vast, but in motion, and the farthest galaxies are receding into silence, not because they are fleeing, but because space itself is pulling them away. Some galaxies are speeding toward each other, defying the expansion of the universe. The universe is expanding, and on large scales, most galaxies are moving away from each other, but not all. Some galaxies, like the Milky Way and Andromeda, are moving closer. Gravity works, and in regions where it's strong enough, it can overcome cosmic expansion. In galaxy groups and clusters, mutual attraction pulls galaxies inward. The Milky Way and Andromeda are expected to collide in about 4 billion years. Other galaxies are also approaching one another, forming pairs, groups, and eventual mergers. The universe may be stretching, but local gravity can still bind galaxies together. These motions remind us that expansion isn't everything. Gravity still carves out its own spaces, little pockets where the rules feel different. And in those places, galaxies aren't flying apart. They're drifting toward each other slowly in a cosmic ballet that plays out over billions of years. The cosmic web connects galaxies across hundreds of millions of light years. On the largest scale, the universe is not a random scattering of galaxies. It's structured. Galaxies gather along long filaments of dark matter and gas, forming a pattern known as the cosmic web. These filaments stretch across vast distances, linking clusters and superclusters into a grand network. In between the filaments are voids, nearly empty expanses where a few galaxies exist. The cosmic web was shaped by tiny ripples in the density of the early universe, amplified by gravity over billions of years. Galaxies form along these strands drawn to regions of higher density. We've mapped parts of this structure through galaxy surveys, and simulations reveal even more. It's a vast three-dimensional web, not made of stars, but of the gravity that holds them. Galaxies don't live in isolation. They're part of a much larger framework, connected by invisible threads across the dark, expanding universe. Some galaxies look like they're spinning out of control. Most galaxies rotate in an orderly fashion, their stars orbiting the center, in predictable smooth paths. But some galaxies show strange behavior. Their outer regions twist, warp, or flare outward. Others have stars and gas moving in opposite directions. These galaxies often formed from mergers or close encounters with neighbors, events that disrupted their structure. The motion inside them becomes chaotic, at least for a while. In some cases, the entire galaxy is warped, like a ripple in a pond. In others, it's more like a broken wheel. Astronomers study these systems to understand how galaxies recover from collisions, and how long it takes for chaos to settle into calm. Even the strangest galaxies tend to stabilize over time as gravity reshapes them and gas settles into new orbits. But at the moment, they are wild. Galaxies are still shaking from past events, slowly finding their balance again. Galactic mergers can take billions of years to complete. When two galaxies collide, it's not a sudden current. It's a slow, complex interaction that unfolds over billions of years. First, the galaxies draw near, pulled together by gravity. As they pass through each other, their stars largely avoid direct contact, but their gas and dust collide, compressing and triggering bursts of star formation. The galaxies may swing past each other several times, their shapes distorted into long tails and low ops. Eventually, they settle into a single system. The result depends on their mass, speed, and angle. Some become smooth elliptical galaxies, others retain features of both parents. Even after merging, it can take hundreds of millions of years for the new galaxy to stabilize. Star clusters are relocated, black holes drift toward one another, and the galaxy gradually finds a new equilibrium. It's not a crash, but a dance, slow, beautiful, and reshaping everything. When galaxies merge, their black holes may spiral together and combine. At the heart of most large galaxies lies a supermassive black hole. When two galaxies merge, their black holes are drawn toward the center of the new system. At first, they orbit one another from a distance, slowly losing energy as they interact with stars and gas. Over time, the distance shrinks. Eventually, they enter a final spiral, drawing closer and faster until they merge into a single, more massive black hole. This final stage is brief and incredibly energetic. It sends out gravitational waves, ripples in the fabric of space-time. These waves have been predicted for decades, and we're just beginning to detect them. Each black hole merger marks the end of a long cosmic journey to massive objects formed in separate galaxies, finally becoming one. It's a quiet event from far away, but it leaves lasting echoes in the shape of the universe itself. Some collisions end in elliptical galaxies, smooth and featureless. Spiral galaxies are full of structure, arms, disks, and dust lanes. But when two spirals merge, the result is often very different. The new galaxy may lose all signs of its past shape, becoming a smooth elliptical blob of stars. These elliptical galaxies are round or oval with little gas and almost no new star formation. Their stars move in random orbits, creating a soft, even glow. The chaos of the merger mixes the stars and scrambles their motion, erasing the organized patterns of spiral arms. The gas may be expelled or heated, halting further star birth. Over time, the galaxy fades into a quieter state. These elliptical galaxies dominate the cores of galaxy clusters where mergers are common. They are the old giants of the universe, built through many collisions, glowing steadily and bearing almost no trace of the drama that formed them. Others leave behind tidal tails of stars, stretching for thousands of light years. When galaxies pass close to each other, their stars aren't flung out violently, but gravity stretches them, drawing out long, delicate arcs of light. These are called tidal tails. They can span hundreds of thousands of light years, reaching far beyond the original galaxy's edge, formed by the competing pull of gravity during an encounter or merger. They often curve outward like wisps of silk, glowing faintly with scattered stars and pockets of gas. Some tails eventually fall back in, while others drift through space for billions of years. These trails are silent witnesses to ancient collisions, elegant and slow, shaped not by impact, but by motion. Some tidal tails even contain enough material to form new, smaller galaxies. Others remain as faint streams, glowing like cosmic brush strokes. In them, we see the memory of past motion, galaxies reshaping each other as the why pass. The Milky Way has absorbed dozens of smaller galaxies over time. Our galaxy wasn't always as large or structured as it is now. Over billions of years, it's grown by pulling in and absorbing smaller galaxies, dwarf systems that wandered too close. Some of these mergers left visible traces, streams of stars, clusters with unusual orbits, and chemical signatures that don't match our native population. Others have been fully digested, their stars now moving alongside ours. Each merger added mass, reshaped the halo, and stirred the motion of existing stars. These weren't dramatic illusions, but slow integrations, gravitational embraces that unfolded over millions of years. Even today, we can trace some of these absorbed galaxies by mapping the movement and composition of stars in the Milky Way's outer regions. Our galaxy is not a singular structure, but a layered one, a collection of many smaller histories folded together into one quiet spiral of light. We are still discovering new satellite galaxies orbiting the Milky Way. The Milky Way is orbited by a collection of smaller galaxies, tiny dim systems called satellite galaxies. For decades, only a few were known, like the Melanic Clouds. But in recent years, astronomers have discovered dozens more. Many are so faint they're nearly invisible. These ultra-faint galaxies contain only a few hundred or thousand stars and are dominated by dark matter. They're hard to spot, lost in the background of the sky or hidden behind the glow of the Milky Way itself. Yet they're important. Each one helps us understand how galaxies form and how dark matter behaves. Some are remnants of early mergers. Others are being pulled apart by our galaxy's gravity right now. These companions move silently around us, tracing long, slow orbits through the halo. The more we look, the more we find. The sky around the Milky Way is full of quiet company we've only just begun to see. Tiny dwarf galaxies can trigger massive star formation in larger hosts. Size isn't everything in the universe. Sometimes a small galaxy passing near a larger one can have a dramatic effect. If a dwarf galaxy collides with or passes through the gas-rich disk of the larger galaxy, it can compress the gas and trigger bursts of star formation. These bursts may light up regions of the larger galaxy, forming clusters and nebulae that outshine the smaller intruder. The process is quiet and gravitational, not explosive, but the consequences are bright and far-reaching. Some of the star-forming regions in the Milky Way may have been sparked this way. The dwarf galaxy provides just enough of a disturbance to set things in motion. It's like a pebble tossed into a still pond, a small event that spreads ripples far and wide. Even the smallest galaxies have the power to reshape their neighbors just by drifting close. Some galaxies exist in compact groups trapped in gravitational dance. Not all galaxies live in sprawling clusters or quiet isolation. Some live in tight groups, a few galaxies bound closely together, orbiting one another in slow looping paths. These compact groups are full of interaction. The galaxies tug at each other's arms, stir up gas, and sometimes collide. Their shapes are often distorted. Some have long tails, others share bridges of stars and dust. Over time, many of these galaxies will merge, forming one larger system. But for now, they remain distinct, locked in a quiet dance, but can last for billions of years. The space between them is relatively small, close enough for gravity to constantly influence their motion. These groups are rare and fragile, but they reveal how galaxies can evolve together in the emptiness of the universe. It's striking to find galaxies bound so closely, like a family of stars moving as one. Galaxies in clusters sometimes smash into each other in chain reactions. In large galaxy clusters, interactions are not rare. They're constant. With hundreds or thousands of galaxies moving through the same region, collisions and close encounters are inevitable. Sometimes one merger triggers another. A galaxy may collide with a neighbor, disrupting its shape, and then pass close to yet another galaxy, spreading the chaos further. These chain reactions can stir up gas, ignite bursts of star formation, and launch streams of stars into space. The largest clusters can act like cosmic mixing bowls, galaxies passing through them multiple times, changing shape, direction, and speed. Over time, many become smooth ellipticals, the result of repeated mergers. But during the process, clusters are full of motion, a slow, graceful turbulence playing out across millions of light years. It's a reminder that even in the vastness of space, galaxies don't move alone. They jostle, combine, and reshape each other in long, quiet collisions. The largest galaxies we know may be the product of countless ancient mergers. Some galaxies grow slowly, others, like the brightest cluster galaxies, grow through a long history of collisions. These giants, often found at the centers of massive galaxy clusters, can be hundreds of times more massive than the Milky Way. They didn't form all at once. Instead, they grew through merger after merger, pulling in smaller galaxies one by one over billions of years. Each added mass, stars, and structure. Over time, any traces of the individual galaxies were smoothed out, leaving a vast, glowing cloud of stars. Some of these giants now sit quietly at the heart of their clusters, surrounded by satellite galaxies still being drawn inward. They are cosmic monuments, the result of eons of quiet consumption. In their light, we see the sum of many histories layered over time into something enormous and serene. We found ghost galaxies drifting between galaxy clusters. Most galaxies live in clusters or along cosmic filaments, but some are found in the vast spaces between, drifting slowly through the emptiness. These so-called ghost galaxies are faint, diffuse, and hard to spot. They may have been ejected during a violent interaction or merger, flung outward into the quiet between clusters. Others may have formed there, far from the usual structures of the cosmic web. Many are nearly invisible, containing little gas and few stars, but they still move, orbit, and evolve, quietly gliding through intergalactic space. We found them by their gravitational pull, by the subtle motion of nearby matter, or through faint trails of stars. These galaxies are reminders that space is not empty. Even in the most isolated corners of the universe, you might still find a faint glow, the light of a galaxy drifting alone through the dark. Some galaxies are nearly invisible because their stars are spread so thin. Not all galaxies are bright. Some, called ultra-diffuse galaxies, contain as many stars as a dwarf galaxy, but are stretched out over areas the size of the Milky Way. Their stars are so sparsely distributed that the galaxy looks like a faint cloud. From a distance, they barely register, like a smudge against the dark. These galaxies may have formed differently, or they may have been pulled apart by tidal forces, leaving only the faintest traces behind. Some contain almost no dark matter. Others seem to have much more than expected. Their very existence challenges our understanding of how galaxies hold together. They are fragile, faint, and easily overlooked, yet they persist. And sometimes that persistence alone is enough to tell a story. Even the quietest galaxies have something to say. Galaxies can leave behind long trails of stripped gas. When galaxies move through dense environments like clusters, they often lose material. Their gas is stripped away by the pressure of the hot plasma that fills the space between galaxies. This process, called ram pressure stripping, can draw out long tails of hydrogen and dust trailing behind the moving galaxy like a wake behind a ship. These trails can be hundreds of thousands of light years long, glowing in ultraviolet or radio waves. Some show signs of star formation, stars born in the middle of the tail, far from the galaxy's core. Others simply drift, cooling over time. Stripping can change a galaxy's future. Without gas, it can no longer form new stars. Over time, it fades into stillness, but the trails it leaves behind remain graceful signs of motion and loss, stretching across space. Like memory, there are ultra-compact galaxies packed densely with stars. At the opposite extreme from diffuse galaxies are ultra-compact dwarfs, tiny galaxies crammed with stars. They can be just a few hundred light years across, yet contain millions or even billions of stars. Some may be the remnants of larger galaxies stripped down to their dens, cores by tidal forces. Others may have formed this way from the start. These galaxies are incredibly dense. A star in an ultra-compact dwarf might have thousands of neighbors packed within a single light year. Their light is intense, their structure tight, and yet they are hard to find because they are so small and easily mistaken for star clusters. Studying them helps astronomers understand what happens when galaxies collide and how structures survive in extreme environments. They are cosmic pressure points where stars are packed into the smallest possible space, glowing with quiet intensity. Others are so diffuse they float like cosmic fog. Some galaxies barely seem like galaxies at all. Their stars are spread out so thinly that the galaxy resembles a faint fog drifting through space. These diffuse galaxies, often found in clusters, are fragile and dim. Many contain almost no gas. Some may be remnants of larger galaxies that were stripped down by gravitational forces. Others might have formed as ghostly systems from the beginning, never building up enough density to shine brightly. From a distance, they're almost invisible, but careful imaging and long exposures reveal their soft light. These galaxies challenge the idea of what a galaxy must be. They're not structured, not bright, and not full of motion. Yet, they are still gravitationally bound collections of stars. They move, evolve, and persist, like mist clinging to the edges of space. They float, quiet and almost forgotten, but still part of the universe's great story. Galaxies may one day be all we can see as the universe expands beyond our horizon. The universe is still expanding, and that expansion is accelerating. Over time, galaxies far away will recede faster and faster until their light can no longer reach us. Eventually, only the galaxies bound to our own, like Andromeda and a few others, will remain visible. Everything else will slip past our cosmic horizon. It's not that the galaxies themselves are moving through space, it's that space itself is stretching, carrying them away. In a few trillion years, a future observer might look out and see only a quiet local group of stars. They might believe the universe is small and still, but we know now that the universe is vast, rich, and full of light, even if that light is fading from view. Galaxies are not just what we see today. They are the last embers of a once visible cosmos, quietly drifting towards silence. We're watching galaxies drift apart forever. Every night sky is a frozen moment in a vast expansion. Galaxies that we see today, bright, distant, and full of history, are all moving away from us. Over billions of years, they will grow more shifted, dimmer, and eventually undetectable. What we see now is a window into the universe as it was, but that window is slowly closing. We are lucky to live at a time when the universe is still readable, when light from distant galaxies still reaches our telescopes, whispering stories of their formation and motion. As expansion continues, the space between galaxies will widen, and each will doctor it into isolation. But even as they move apart, the memory of their light remains. Every image, every spectrum, every map we make now is a record of a changing sky, and each receding galaxy leaves behind a silent echo of where it once was. Galaxies tell the story of how the universe grew up, from the first tiny clouds of gas after the Big Bang to the vast structured systems we see today. Galaxies are the backbone of cosmic evolution. They show us how matter organized itself, how stars formed and died, how black holes grew, and how light spread through space. By studying galaxies at different distances, and therefore different ages, we can reconstruct the universe's history. Early galaxies were chaotic, full of fast star formation. Later ones grew larger, more stable, more ray-structured. Galaxies are shaped by gravity, but also by time. They carry the marks of every interaction, every burst of light, every quieting moment. They evolve, change, and settle like all living things. And in that evolution, we see the universe growing from youth to maturity. The sky is not just a static canvas, it's a time lapse, and galaxies are the brush strokes. Every galaxy is a cosmic archive and a mirror of what we might become. Inside each galaxy is a record of stars born and gone, of collisions endured, of black holes fed and faded. Their stars preserve the chemistry of ancient gas clouds. Their motion reveals past interactions. Their shapes reflect long histories of growth and quiet change, and because galaxies form from the same laws that govern us, they also are reflect what's possible. Where we see spiral arms, we see structure. Where we see starbursts, we see transformation. And where we see quiet halos, we see long, peaceful aging. Galaxies are not just beautiful, they are meaningful. They remind us that everything changes, that memory can last across space, and that light can echo long after its source is gone. In the end, a galaxy is both distant and familiar. It holds the past, shapes the present, and hints at futures we can only imagine. Thank you for spending this time here, for listening, wondering, and drifting quietly through the galaxies. We've wandered across spirals and giants, through mergers and halos, past quiet dwarfs and glowing arcs of ancient light. Some galaxies shone bright, others barely whispered, but each one here will a story, a piece of the universe written in stars. And now the sky is quiet again. The facts may fade, but the feeling of distance, of time, of being small beneath something vast that stays with us. So let your faults go gently. Let the motion of galaxies become the rhythm of rest. No more questions tonight, no more discoveries. Just space, just calm, just sleep. And if you happen to still be awake, you can go ahead and watch the next video now. But if your eyes are already closing, that's perfectly okay too. Good night and sweet dreams from the stars.